Okay, so a couple definitions. I sort of distinguish between a stability study and a shelf life study because while often we use stability studies to estimate shelf life, that's not the only way to get a shelf life estimate. So this is a little more general talk about both. I view a stability study as like an experiment where the goal is to understand essentially the stability of the product over time. And presumably we're doing this on a product that we believe degrades or ages, and like food products and drugs and things, and we'll look at some of these examples. And we want to understand the nature of that degradation and often use it to make predictions. Now, shelf life, I'll just define as the length of time that we are able to store our product without it becoming sort of unacceptable or unfit for use or consumption. And we'll see, when we define shelf life, we're going to kind of use a statistical definition where we have a confidence and a sort of a proportion conforming at the shelf life. As I said, other methods besides the stability study can be used to actually estimate the shelf life, and we're going to be talking about one of those. So common applications for shelf life problems, right? Basically anything that degrades over time. Foods and beverages, medicines, pharmaceuticals, medical devices, so on and so forth. Now, I'm sure we come from different industries, but we're all consumers of foods and beverages. So just to kind of illustrate, sometimes we have perhaps two different shelf life dates or two different expiration dates. Like in foods, we often see a use by and a best by date. So use by is, at least in that industry, is really geared toward you should use this product to be completely safe, although there's obviously usually some safety margin in there. But best by, you usually see on products that aren't necessarily going to become harmful beyond the date, but may not be as high quality or nutritional value, those kinds of things. And then that's certainly true of like shelf-stable products like canned goods and frozen products. Usually, those will have a pretty long shelf life, but there may be changes in sensory issues or nutritional degradation, those kinds of things. With pharmaceuticals, we're often looking to ensure that a patient will consume the drug. When they do, that it has full potency and full efficacy, and of course safe to use by that expiration date, which is based on the shelf life estimates. So just some examples of some common industries and types of products. Now, when you do these studies to estimate shelf life, you have a couple of options. You could refer to a direct study as a study that would be conducted sort of at the normal storage conditions. So however your consumer would typically store, and that may be a range, right? The study's conducted at those conditions. The one issue with trying to do that is it may involve a pretty lengthy study, right? Because you can't sort of shorten the time. You have to just sort of wait for things to happen. Another possibility is to perform an indirect study or an accelerated study. And then, of course, these kinds of studies are conducted at higher stresses. Could be temperature, humidity, loads. This is analogous also to a method called accelerated life testing in the reliability world. And the reason we do this is to shorten the time that it takes to reach a non-conforming product. And then we need either a model or some kind of conversion to correlate times, sort of the shelf life we observe at the accelerated conditions to what those would equate to at normal usage conditions. And if you're not sure scientifically what that is, then you can do a kind of a more involved experiment where you vary the stresses and observe aging times, and then model the sort of the distribution of aging times to where shelf life is reached, like till failure is reached, as a function of the stress. And then you could predict what the equivalent times are at the normal use condition. One issue to watch out for when you're doing accelerated studies is to take care not to induce failure modes or mechanisms that you wouldn't normally see at normal storage conditions. Okay, so just to kind of review shelf life and stability studies. A shelf life study, the goal is to estimate the time at which the product no longer is fit for use, becomes non-conforming. That's the goal. Now, stability study purpose of it may be to estimate shelf life, but more generally speaking, a stability study is a study where we simply are trying to understand whether the system is stable. Maybe it's just a manufacturing parameter and you're just looking at data over time, like what we would do on a control chart, with the expectation that the process should remain stable, and we're trying to detect changes so we can react. If we're specifically looking at stability because of shelf life situation, we're trying to estimate the shelf life, then we naturally would expect that there is some degradation, and the purpose of the stability study would be to model the rate of degradation over time so that we can predict how long the product can sit before it's no longer should be utilized. Another designation of types of studies is the following. I'll call a simple study sort of what we're going to be talking about today, where we're going to fix the conditions, like the storage conditions. We'll use different samples, potentially from different lots, but when we conduct the test, we're not varying the formulation or the packaging or how we're storing it. We're basically fixing everything and trying to predict the shelf life under a defined set of conditions. I'll call it a simple study. However, we may be interested in understanding shelf life as another performance characteristic of our product, just like we would, whatever that product is supposed to do, like taste and texture or tensile strength or viscosity or whatever the factors are in our product. Maybe shelf life is going to be another thing that we want to consider in how we design the product or the packaging, or we want to understand how storage conditions. So you could do a more involved experiment where your response is shelf life along with maybe some other things, but you're going to be varying factors that could be involved in the formulation or the packaging, materials or thickness or those kinds of things, or storage conditions. So I'll just say that if you're going to do this kind of a study, I would strongly encourage you to look into using a methodology called design of experiments, or DOE, because rather than sort of haphazard trial and error approaches, DOE is a very structured, balanced approach that allows you to build predictive models that let you understand the relationships between these input factors and an outcome like a shelf life. And also, they're naturally set up to also be able to understand the way certain factors, inputs, interact with each other. So your models will not generally be just a bunch of linear combinations of different factors, but to reflect the reality of the world is that the effect of one factor on the response may depend on other things, and those have to be included in your model as interactions between variables, and you would see those as like product terms in your model. All right, so in any event, these are simple and multiple factor studies. Now, before conducting a shelf life study, I strongly encourage you to do some planning. And there's a lot of things to think about in planning a shelf life study. And things like we want to make sure we know what the objective is of the study. Hopefully it's to estimate the shelf life with a certain precision and confidence. but more importantly, we want to understand what are the likely resources we're going to be needing in terms of measurement systems, in terms of time, in terms of chambers. What are we going to measure? How are we going to measure it? How frequently are we going to measure it over time? What does our measurement system look like in terms of its capability? Is it repeatable, reproducible? Do we need a better measurement system? How are we going to analyze the data? Are we going to model different failure modes? If we anticipate there's more than one, are we going to model them separately, or just treat every failure as a failure and kind of lump it all together? On and on, right? So there's kind of a lot to consider, and I think this webinar will at least maybe sensitize you to some of these things, especially around analysis methods and perhaps how you would think about sample size and some of these kinds of issues. Okay, so one thing that's clear, we need to make sure we define what is it we're going to assess over time. Like, we don't just start aging the product and then decide, well, what are we going to measure, right? We need to know what are the likely failure modes and how are we going to measure them. So here are some examples. And then, like I said, we have to think about, do we want to model failure modes independently and then combine results into an overall shelf life? What I tend to see is a lot of people will just, if they have different attributes that they're monitoring, they'll calculate the shelf life independently of the different attributes or characteristics, and then just go with the minimum value, the worst case. That's actually not being very conservative, because you're kind of ignoring, picking the worst of the different models is good, but you're just kind of assuming that that's the only failure mode you're really going to see. And the reality is, if you want to predict shelf life, you should account for all the different ways in which the product may fail. To kind of illustrate this idea, I've got a couple of pictures here. So on the top part, I'm showing a distribution of, let's just say, time to failure, time to when the product becomes unfit for use. Okay. So, and I have three different distributions corresponding to when failure mode A occurs, B and C, and time is on the x-axis here. So the curve kind of represents where the curve is high, we expect more failures to occur, but by the time we reach like towards sort of the end of the right tail, I mean, it goes to infinity, but to the point where the curve is pretty much flattened out, that means pretty much 100% of the population will have failed for that failure mode. So in the top picture, we would expect, if we were just testing to failure and we wrote down the failure modes and the times, we'd basically getting a bunch of failure times for failure mode A, because essentially pretty much everything's going to fail for A before the B's even kick in. Now, on the bottom graphic, it's not that case. There's a lot of overlap between these curves. So sometimes we're going to get a failure due to A and sometimes due to B. And, in this case, if you had two different shelf life estimates, there's one approach is to take the worst case, and the other is to correctly combine these estimates into a single shelf life estimate. And one of the methods we're going to talk about, that's sort of straightforward, and we'll see how that works. Now, one idea with this is if we have like the two failure modes, A and B, we say that they follow a competing risks model. And what does that mean? I mean, if we have a failure for one failure mode, and let's say the unit has to come off a test now, it'll never fail for the other failure mode, because let's just say it failed for A. However, we should consider that at the time it failed for A, it survived that long and did not fail for failure mode B. So again, if you're modeling each failure mode independently, you would have to take into account not just the failure times for each failure mode, but also the known suspensions or right sensor times that the unit survived without a failure. We'll see this a little bit more later. These are just some examples on the food product of potential failure modes that you could consider, looking at? I mean, it's kind of a lot, but it could be color changes, texture changes, maybe rancidity, so loss, undesirable aroma, those kinds of things, loss in flavor. And then these are just some of the factors that might perhaps affect when those failure modes actually kick in. Okay, a couple more before we get into the methods themselves. I want to define fitness for use, since I kind of use that in the definition of shelf life, so I use unfit for use. But we specify that usually through some kind of specification limit or perhaps operational definition if the failure mode is more subjective, like a smell. You'd sort of have to have some kind of definition if you can't measure it. In this webinar, we're going to be focusing on really more quantitative type characteristics that we can measure. So we'll essentially be able to measure and compare to our spec limits to see, is it fit for use or isn't it? And like I said here, we might have objective measures where we have quantitative data with capable measurement systems, or it could be more subjective. If you're looking for when things start to smell bad, different appraisers may have different sensitivity, and so there's going to be perhaps more variation in those kinds of measurement systems. So then, how are we going to define shelf life? So shelf life is not, in my view, not so simple as just saying it's a 1-year shelf life or a 3-year shelf life. I mean, ultimately, that's what the customer is going to see through an expiration date. They're going to say, well, this bottle of aspirin has, another 2 years on it, so I'll buy this size because I think 2 years I'll have enough opportunities to use this up. But really, when we're defining shelf life, we're going to be a little bit more specific in terms of we need to specify a proportion of our population that actually could be considered to not meet spec at the shelf life. Okay? And the number's not going to be 0%. It could be very small, but because we're dealing with continuous models and distributions and making predictions, you wouldn't get to like 0 probability until you reached infinite time, for instance. So we're going to be selecting some proportion that will permit to be out of spec at the shelf life. I mean, it might be 0.01%, something very small. Of course, that's going to depend on the risks involved. Yeah. So more to come on this. So let me illustrate this idea with a picture. Let's suppose we're looking at viscosity of some kind of, an oil that we're storing. And let's suppose over time the oil will naturally become thicker due to some degradation of some of the components. And at time 0, let's just say the distribution of viscosities kind of is over here. And this is not time, this is a viscosity scale all at a given time at 0 months. And let's say our upper spec limit is here. So, for a newly produced product, there's some variation, but it's all, very well conforming to the specs. Chance that we'd see something this far out from this curve is minuscule. But then at 6 months, if we looked again at a distribution of viscosity values from our aging products, the curve is shifting. The mean is shifted, same variation here, but still we're, well within spec. But let's just suppose at 12 months, we see that some of this curve now exceeds the upper spec limit, and specifically, this red section has an area under the curve of 0.05 or 5%. So if we define shelf life as the time at which 5% are expected to not meet spec, then our shelf life estimate in this case would be 12 months. Now, here's the issue though. All of our estimates that we're going to be making, any estimates you make from sample data, have uncertainty. And we quantify this uncertainty through the use of confidence intervals, or in some cases confidence bounds, just a one-sided bound. The uncertainty is a result of the fact that there's the randomness to the sample we happen to take, and there's also variation. So if there's a lot of variation from sample to sample or from unit to unit within a sample, we'll have more uncertainty in our estimates. And if we don't have a lot of data, like small sample size, again, all these are going to contribute to uncertainty. So again, we use confidence intervals. A confidence interval is basically an interval around the point estimate against the estimate we make that will contain the true value with some level of confidence, which is kind of equates to probability. You could think of it this way. If you were to estimate some parameter, something for that you have to take data to estimate, and you estimate it, and then around each point estimate, you construct a 95% confidence interval. Let's suppose you repeated this. You took 100 different samples, and around each sample estimate, the estimates are changing, but the confidence interval is calculated around that estimate. Now, let's suppose this line happens to be the true value of what you're trying to estimate. We would expect that not all of the confidence intervals, 95% confidence intervals, are going to contain the true value. Specifically, out of 100 intervals, we would expect roughly 95 of the 95% confidence intervals to actually include the true value. 5%, like this one as an example, would not contain the true value. Now, instead of constructing a confidence interval where there's a range that we define that contains the true value with 95% probability, therefore there's 5%, 2.5% chance it's bigger than the upper bound, and 2.5% it's lower than the lower bound. Many problems, including shelf life problems, typically use just a one-sided bound. So if you just had a lower spec and you wanted to make sure that your product was not below lower spec, you might just look at the lower confidence bound. The difference here is that all the error is on the lower side, all 5%. So it pushes the confidence bound closer to the estimate, to the middle, than it was in the two-sided case. So just to come back to this example we looked at with the 12-month shelf life, when I showed you this picture, when we reach the time at which 5% is non-conforming, the point estimate would be 12 months, but the actual lower confidence bound, say 95%, is going to be less, maybe just for example 11.3. We'd have to calculate it based on the data. And then if we wanted to be 99% confident, well, what happens to this lower bound? Well, it gets further away from the 12-month estimate. It's to be more confident that 99% of to the right has a 99% chance of containing the true value. We have to have a lower bound, right? We have to have more area. So just to give you some appreciation of how this is going to work. Now, in terms of spec limits, just a quick word about those. I've seen sometimes people who do a shelf life study where they don't really know what the spec limit should be. So instead they say, well, we'll just do like a hypothesis test, and as soon as we see that there's a statistical difference between the baseline times zero value and what we're seeing later, as soon as that becomes statistically significant, we'll call that the shelf life. I don't think that's a very good idea because statistical differences may not be practically important. They may have no value or meaning to our customer or product performance. And also statistical differences are highly dependent on the sample size. In other words, maybe there's a practical difference before you would even find a statistical difference that you need to know about. Or probably more likely, the statistical differences that you maybe could detect are not very important practically. So just keep that in mind. All right, so we've kind of finished this introductory part of the webinar with a lot of the concepts. And so what I want to do is start going through some of the methods for analyzing or how we would conduct these studies to estimate the shelf life. So there's really two main methods I want to talk about, but the first two kind of go together. There's the sort of what I call life data analysis or reliability analysis approach, which would be a direct study, and then accelerated life testing would be an accelerated version of that, with where you're making things go quicker. The second main approach is using conducting a stability study, where you're sort of measuring a parameter and observing its degradation, and then usually fitting a regression curve or line to that degradation, and then using that to predict when the values are going to reach a certain point that we'd call a failure. And then we'll talk about how to accelerate that kind of a model as well. All right, and as I kind of go through this first approach, I'll try to reiterate a few times as to what would sort of lead you to use this method. I'll just say at the beginning, one reason why you would use this approach is where you've got different failure modes that you want to really correctly combine into one shelf life estimate. The second reason why you would probably use this approach would be if you really can't measure something quantitatively. Let's say you're just putting a product, aging a product, and you open it up and you see if it looks right or smells okay. And it's either is or isn't, so it's pass fail. Okay. So because the data there would be sort of pass, 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 and at some point you finally see the failure, that's like not conducive to fitting a regression line too. So with that approach, we're really going to try to obtain some failure times, actual failure times, or at least ranges that include the failure times, and then use that to kind of estimate this time to failure distribution and calculate our shelf life on that model. So with that said, let me kind of run through this. So under this approach, we're going to test or age our units. This is under normal conditions. And we're going to use the standard, this methodology is very standard for reliability engineers to estimate the reliability of a product. The only difference is their products are in use, getting cycles or loads or whatever, and we're trying to estimate when they're going to fail, like wear out, for instance. In the shelf life problem, the math is the same. We're just talking about modeling the time, the aging time that a product how long could it actually wait before it's actually consumed or used. It's usually like a one-shot use type of thing. Now, so we're going to try to collect these failure times, but we're also going to pay attention to units that don't fail for a given failure mode, either because we reached the end of the test and they didn't fail, or maybe they failed for some other reason, and we're going to still count that as a non-failure for that period of time for the failure mode that we're modeling. This gets involved with censoring, which I'll talk a little bit more. One type of censoring is called interval censor, which is common like when you're testing in a chamber and you're only checking the units like once a day or twice a day, once a shift. And if you see a failure, you don't know exactly when it failed. You just know the last time I checked it was okay, and at this time it's now a failure. So when you're using this first method, it's important to understand how to think about collecting the data. And not just, of course, we want the failure times and exact failure times if we know them, but there's some scenarios where we wouldn't know the exact failure times. It could be, again, like we test for a certain period of time, let's say 1,000 hours, and the unit doesn't fail. And then we're not going to ever go behind 1,000 hours. Maybe most of the units fail prior, but here we had a unit that didn't fail, so we're going to just call it right censored and say, all we know is that the failure time exceeds 1,000. That's called right censoring or suspension. Left censoring could happen if a failure's occurred, but maybe you don't know when it occurred. You just know it occurred prior to some known time. So left censoring is actually a failure, it's just to the left of some known time. And then interval I talked about. That's a failure that's occurred between two known time points. And there are ways to sort of account for these kinds of censoring in the calculations. Now, the way this methodology works is we collect our failure data. It could be So, and to do this, you're going to need some failures, right? You can't just have all survivals and like expect to know when is the shelf life, right? Because nothing has actually failed. So once you have your failures and plus some sensor data typically as well, you can try to fit a model to the failure times. So you'll go through what's called distribution fitting procedure. This is an example of trying to fit a bunch of failures to 4 different models: Weibull, log normal, exponential, normal. So, you know, I know a lot of you probably have seen or used the normal distribution, and we do use it a lot for certain things, but, you know, times to failure often end up being not symmetric. They're skewed. So we have to be a little careful about imposing a bell shape because our data may have this kind of skewness to it. And we don't have time to go into the details here, but basically we're looking for fits on these plots that look pretty linear. The dots line up. We also look at some what are called goodness of fit statistics, and in this case, the smaller value is the best one. So Weibull is like the best here, and then log normal also looks pretty good. So we could use this Weibull model. This is called a Weibull probability plot to then think about calculating our shelf life. So let's just see how we're going to get to the shelf life. So suppose that straight line that we looked at is actually representing this distribution. So essentially what we're saying is if we tested a whole bunch of products to failure, they would fail between time 0 and time 1500, and they would sort of follow this shape. Most of the failures are going to occur in here. You know, some are going to last longer, and a few are going to make it really long. But it's this sort of model, probability model. Now, if we wanted to know, like at a certain time, let's say time 1500, what's the likelihood that units are going to still be okay at that time? How would we find that probability? Well, this gets back to why you learn calculus, right? The probability is equal to the area under the curve. So if we're talking about probability that we survive 1500 or more, it's this area to the right. So you could integrate this Weibull function and get this area, which looks like it's about 16%, 0.16. So this side would be the probability of failure. Okay? Now, you could look at a function called the survival plot, which actually is just the area to the right as a function of time. So at time 0, chance of survival is 100%. So we start at 100%. And as we go along and look at the area to the right, the area to the right starts to fall until eventually, you know, we're at time 1500 and the area is down here around 16%. Okay. And then way out here, the area to the right is almost 0. So it goes down. All right. I've just kind of blown up that survival plot and looked at time 1500 to show that that area to the right of our probability curve is at 16%. Now, shelf life, we're usually put in terms of not survival probability, but failure probability. So let's suppose this is actually a different curve. Let's suppose here's my curve that I fit to my time to failure data. And I find that I want to define a shelf life such that it's the time at which I'll allow 5% of my product to not still be, you know, fit for use. So I want to find the time on this curve so that the area to the left is exactly 5%. And I see here that it's 138. This is also called in the reliability world the B5 life, or the 5th percentile, time at which 5% fail. Now keep in mind, this is the point estimate. Just again, to illustrate that, if I go to my survival plot, 5% failing is equal to 95% surviving, right? So on that survival plot for that function, 138 would be right exactly where this curve hits 95% survival. Okay. Now, as we talked about earlier, that's a point estimate. We really, when we're calculating shelf life, we should account for the uncertainty in our estimates, which allows us to say, this is my shelf life with a certain high level of confidence. So you could do a 2-sided confidence interval around the actual survival curve, which, you know, is one way to do it. I'm going to propose that we just look at the the appropriate bound. So in this case, here is my curve. In this bottom one, I don't know why it does the same color. This is my lower 95% lower confidence bound. And the 95%, where we reach 95%, this was the 138 on the actual line, right down here. But where the lower bound crosses or falls to 95% is actually a little less than 100. It's 94 days. So that would be my shelf life estimate. It'd be the time at which I'm 95% confident that no more than 5% are failing. Okay? Don't confuse the confidence level, which happens to be 95%, and the reliability, which is also dropping to 95% here. This happens to be the same in this example. So that's essentially, I left out a lot of steps, right? But basically, you're gonna have to measure some parts to failure, or age parts until they actually fail, until you see the smell, or until you measure something that's out of spec. And you have to get a number of failures. I'd probably want, I don't know, between 5 and 10 failures to get a reasonably good estimate of. 10 is a lot better than 5 actually, but to get a reasonably good estimate of what the distribution looks like. And then you could make some shelf life estimates. Okay, real quickly, we could extend this life data analysis to do what's called accelerated life testing. And I'm just going to give you the idea here. This is where you would age the units under stressed conditions and, again, measure time to failure, but you have groups of units under different stresses. And I'm going to assume that we don't know the correlation between time at a high stress and time at a low stress. We have to derive it. So obviously, you're going to pick accelerating factors, perhaps temperature, humidity, or both. You could have more than one that would shorten the time to failure. And then we're going to build a model that will extrapolate, first, that will predict the relationship between stress and time to failure, and then extrapolate to the normal aging conditions. So it looks like this. You're going to, let's say this is our use condition, meaning this is the normal, let's say, temperature at which we're going to age our products. The products are going to be at maybe like room temperature. But we're going to age them groups of units at a very high temperature, medium high, and just high. And we'll observe these, at least some failures so that we can understand the probability distribution of failure times at these different stresses. Then we could actually do a type of regression that's not quite the standard regression, but it can account for non-normal data and can also be appropriate to a specific percentile, like the 5th percentile or 1st percentile. So we could predict maybe the shelf life or the time at which 1% will fail at the use condition based on what we've observed at the stress conditions. Lots of different possible stress factors. Again, this methodology is heavily used to predict reliability of products, at least in some kinds of products like electronics, given the time it would take to test reliability at normal conditions. This is an example of some data and the distributions, and then what we call the structural or regression model that allows us to really derive the distribution that we didn't observe, but derive what it would look like up here at some normal use condition. And so what this model does is allows us to estimate the distribution not at just one temperature, like a use temperature, but as a function of temperature. Okay. We're now ready to kind of move into the second approach called, and we're about sort of like halfway through the webinar now. So this second approach is what we call a stability study. And again, we'll start with how to do one under normal use conditions, and then kind of briefly talk about how you could do a stability study under accelerated conditions and how you might do that modeling. So what we're going to do here is we're going to monitor and measure degradation of one or more characteristics over time. Maybe a failure, but typically not to failure. Part of the reason you're doing this is because you don't want to test all the way to failure, but you're going to observe enough degradation to fit a model, and then use extrapolation to make predictions. Now, obviously, when you extrapolate, it can be a little risky because you're going to assume that the model that you're fitting to what the data you do have holds true. Like if it's a straight line, you're assuming that it's still going to stay linear. That may or may not be true. Now, we'll talk a little later about how to, what are some good practices to validate the models. But another reason why we're calculating confidence intervals and basing shelf life of confidence intervals is that when you extrapolate, right, you have, even if you have the right model, there's more uncertainty in the estimates because you're trying to make a prediction further away from when you actually have real data. So even if you have the, you know it's a linear model, but maybe your slope is, because you don't have data all the way out there, maybe your slope is, kind of not very precise. Had you had more data, you would have had a different slope. So that sort of uncertainty will grow as you begin to extrapolate. So these stability studies are essentially going to allow us to assess the degradation and model it over time. I'm going to assume here that we're dealing with quantitative values, and then we'll fit a statistical model, namely a regression model, to the data and extrapolate as necessary. And then we'll basically see when does that regression line, or more precisely the confidence bound around that regression line, when does that actually reach, when is it predicted to reach the max or minimum acceptable value, in other words, our specification limit. Now, so we're going to be going through a bunch of scenarios, examples of this. But before we do, to keep putting it off, I want to just say a word about standard regression models. So what is regression? It's a way to take some data, like on a scatter plot, where you have two variables. This example here is a study that was done to try to relate the number of hours per week children of a certain age watch TV versus their score on, say, the SAT or some standardized test, achievement test. And of course, there's a lot of scatter in the data, but you could fit a model, sort of find a best fit model that minimizes the errors here, the differences between these points in the line. And that directionally captures the relationship between TV hours and score. In fact, so here we're fitting a linear model, which is the most simple model we could imagine, where the score is equal to some intercept, which predicts the outcome at 0 TV hours, highest predicted score. And then for every increase in TV hours, this model predicts a reduction in score of about 54 units per hour of TV watch. That's the slope. Okay. And now the other thing is the regression models assume that the data at a given X, that the responses are normally distributed. And so what this line represents is the mean of a normal distribution. Mean is changing as TV changes. That's what a regression model does. So if you're using standard regression, you need to make sure you check some of these assumptions, that the errors are normally distributed. And another one is that the errors sort of don't get larger as we get to larger values, that's consistent over the range. The reason I bring this up is that it's very often in reliability problems or aging problems or shelf life problems, you may find that the variability is not normally distributed in the y direction. It's skewed. And maybe other models like YBO or log normal. Now, that doesn't mean you can't do these models. A lot of people will work on maybe transforming the data to make it fit if they need to. Or you could actually fit more sophisticated regression models. You usually need some kind of reliability software to do that, but there is a version of a regression model that can handle other distributions other than a normal distribution. That's what this is saying here. You might need some reliability software. Okay, so now we're really ready to look at some examples. Let's take a look at some iterations where we look at some stability data and use it to predict shelf life. And in my examples, we're going to be extrapolating. I don't have the data going all the way to the failure point. And we'll look at some different kinds of regression models. So the scenario is this. I've got some data here in a column, measurement data of the, it's a chemical, it's some parameter in the chemical variable that measures degradation of some sort, or that's changing over time. And I've got a bunch of different samples, and I can, maybe this represents different batches. And so I'm taking measurements over time, time 100, 200, 300, 400, 500, and then from that sample, and then repeating it for some other samples. So I've got 5 samples. And let's just suppose 50, you can see the values are sort of trending upward within the sample. 50 is considered like an upper spec where I wouldn't want my customer to use the product if this substance is now over 50. So I'm using, in these kinds of models, I'm using Minitab, as was the previous as well. So in the regression module, every statistical software package will have regression modeling. There's actually a type of specialized regression option here called shelf life, regression, shelf life plot, which will, make it easy for you to get the shelf life. It actually reports it right on the plot here. But what it's doing is it's plotting the data points that we observed at time 100, 200, 300, 400, 500. So these come from different samples. And then it's fitting a regression line. For now, I'm just going through the default. It's fitting a regression line through the mean, which models the mean of the data versus time, the mean measurement versus time. And then it's also drawing a dashed line here, which you can see is close, and then it's sort of flaring out here. That's our 95% upper confidence bound around the mean. Okay. Now here's the equation. All right, so it's just in the form of y equals mx plus b, and it seems to be like a pretty reasonable fit. And anyway, the shelf life then is going to be defined as the time, not where our mean regression line crosses 50, that's out here somewhere, but where the upper confidence bound, right? If you have an upper spec, we're going to look for where does the upper bound cross 50. And you can see here, it's right here. And that time, if you bring down, is about 880 units. Now, how would we interpret this shelf life? I drew a mean regression line. So again, imagine that the data really follows, the actual raw data follows like a bell curve. So at this time, we're 95% confident that the mean is no larger than this value. In fact, let me shift the curve up a little bit. So at a 95% confidence interval, we think that that's the highest the mean could be. But notice, that predicts that some of the units are actually going to exceed this shelf life. And how much? Well, the mean of a normal is the same as the median. So this is actually 50%. This is probably not how we want to do the shelf life. Let's look at the kind of the statistical output. So this is the model. This is the coefficients of our model, the intercept and the slope. Here's the equation. And then here's the spec limit. And it says, okay, the shelf life equals the time period in which you can be 95% confident, because I specified 95%, that at least 50% of the response is below the upper spec, meaning that it meets requirements. So we're 95% confident that half are going to meet spec and half are not going to meet spec. I like the confidence level. I don't like the fact that we're allowing 50% to not meet spec. Okay. So I want to rerun this. And one of the options, I'm not showing you all the menu options, but one of the options is to not just go with the default of the 50th percentile or the mean line, but specify some other percentile. You could say 99.9 or 9, so I just picked 90. So now my regression line is it's the same slope, but it's shifted up so that it's sort of going through the predicted normal curve such that only 10% is above it. So up here, the shelf life you can see now has dropped from like 880 to 797. It's earlier because we're being a little more conservative. We're only going to tolerate 10% of our units to not meet spec with 95% confidence at the shelf life. Okay. So there's really two things to worry about here or to specify. It's the confidence level and the proportion that you're willing to tolerate will not meet spec at the shelf life. And it can be as small as you want. Of course, if you go really, like we asked for the 99.999 percentile, the problem is what? This is going to be further and further from the line, and so we're going to end up with an earlier and earlier shelf life. So you have to see how far you can really want to go. Again, the session window output, and Minitab is getting pretty good about not forcing you to interpret all the outputs. It's telling you exactly what the shelf life is and what is it actually telling you. It's a time at which you're 95% confident that at least 90% will meet spec. Okay, now recall there were some requirements to use these basic regression models. One is that the errors or residuals are normally distributed. So they give you this normal probability plot. I don't want to go too much into this because of the time, but we want to see like these dots look kind of follow a mostly straight line, and this looks great. Also, the variation should be roughly equal around 0 and, within reason, within certain bounds, not like getting much wider out here and very tight here. In other words, we want the model to predict roughly equally well across the range of fitted values, also across time, and this looks fine. Now, another scenario I want to bring up is, for any of you that are involved in FDA, specifically pharmaceuticals, I know I have some experience doing some shelf life studies where they put out a guidance document called Q1E. It talks about standards for conducting stability studies and estimating shelf life of pharmaceuticals. And they sort of require or suggest that you really need to ensure that you test at least 3 unique batches and then determine through a test whether or not you're justified in sort of pulling all that data together to produce a single shelf life estimate. Because if the batches look statistically different with some level of confidence, then they'll suggest that you have to model them separately and then use the shelf life that comes from the batch that is the worst, that predicts the worst shelf life, which could be problematic if you're trying to achieve a certain shelf life and now you have to use less data because you can't combine all the data from 3 batches, which is already hurting you from lack of precision. And then you also have to take the worst case, right? So let's just take a look at a couple of examples for this. So I've modified the example slightly. Spec limit's still 50. The data's still trending upward. But now I've got like 3 batches of data, batch 1, batch 2, and batch 3. And I have multiple measurements from within each batch. So when I analyze this data, in the statistical output, there's a table here called an ANOVA table. And because I'm not just looking at how data varies with time, I'm also want to investigate, are there batch-to-batch sort of systematic differences, and are there batch-time interactions? So what does this sort of allude to? Batch-to-batch differences, I'm thinking of like a complete shift up and down in my line. Like we start at a completely different spot. Time batch is looking at, does the effective batch depend on time? Like that would be like if you have a very different slope, from one batch to another, then a time batch interaction would be statistically significant. So without spending a lot of time explaining hypothesis testing and p-values, let me just say this. In these model building output, we look at the p-value, okay? And what we're testing here is whether these terms are statistically significant, whether they affect the variation, the overall variation we're observing. And so if the p-value is low, like let's say less than 5%, we would then say there's sort of overwhelming evidence that we want to reject the statement, the null hypothesis that the batch is not significant. And the same thing with the time batch, not significant. Now in this example, these p-values are high. So what actually happens is, because this p-value is so high, the time batch is the highest one, because it's above our cutoff, which in this case with the FDA suggests we use, usually we think of a cutoff around 5%. The FDA suggests no, sort of penalizing you. If there's even a 75% chance that there are batch-batch differences, they're going to make you report them separately. Normally, we assume we have a higher bar. We can get into that on the Q&A if you want. But so what happens here is it removes the time batch since this p-value is greater than 0.25. And then it re-estimates everything. And this 0.948 is still high. It's 0.946. So then it comes out. And we're just left with time, which very low p-value indicating that time is important. Time explains variation. Well, that shouldn't be a surprise if you're doing a stability study. So the upshot of all this, because these p-values are high and that these terms came out of the model, it's basically saying that the batch and both the intercept and the slope are really not statistically different between the different batches. Feel free to go ahead and pull them together. So then in our graph that it produces, while it shows the data from the different batches in different colors by default, it's using all the data to fit this regression line. And it's the same old thing. I just went with the default. So this is actually the mean regression line. I'm not using the 90th percentile. Then this dashed line is the 95% upper bound around that mean. And so the shelf life is up here at around 920. Okay. So, you can't just assume that all the batches are pulled. You have to check those tests of significance, whether they're significant or not. Now, I put together an example where you can't get away with pulling the batches. So here we have similar setup. When you analyze the data, this was extreme in the other direction. Both the batch, just the batch p-value is very low. It's less than 0.0005, so it's just rounding to 3 zeros. The time batch is a high p-value, very high, very close to 1. So that suggests that the slopes are very similar, batch to batch. So you don't need a separate slope for each batch, but you do need a separate y-intercept. Bottom line is you cannot pull the batches here since at least one of them is rejected. And so you're going to get these shelf life estimates for each batch. So this is batch 1. It predicted 928. Batch 2 had a much steeper slope. Sorry, not a steeper slope, but it started higher. We'll see this in a minute. Slopes were the same, basically. This shelf life is 815, much earlier. And then batch 3 is 1010. That was the best one. So when you bring it all together, we're going to base the actual shelf life on the batch that has an upper bound, 90%, that crosses the spec limit first. Like these batches predicted shelf life estimates that were, over here. But we're going to go with the worst case, which is the red batch 2. That's our shelf life of this product, based on the worst case batch. Okay, so we've got about 15 minutes left for Q&A. I got just a couple other iterations of this, or at least one more, and then I want to talk about a few other things. So I've gotten rid of the batches now. I'm just back to like the 5 samples. And I wanted to talk a little bit about, hey, just like the world is not normally distributed necessarily, it's also not linear models don't explain every relationship that we see. So I just want to illustrate that. So it's a similar idea. The values are going up. We've got data from different samples. We know the times. The spec limit's 50. But in this case, as we're going to see, a linear model does not adequately describe the data. So I went ahead and just used the shelf life plot. Now, in this software I'm using, Minitab, the shelf life plot always is going to fit a linear model. And you may look at this and not see anything wrong with it, but my eye is telling me that although the straight line is touching all the points in each time, it's sort of like at the bottom of the data early on, and then it's at the top of the data, and then it's kind of back to the bottom of the data again. This will be more visible. The problem will be more visible on the residual plots. But I kind of see a relationship that's not very linear. Maybe it's, if I took the first 3 times, I'd see like this slope, and then that one plus the next 2, it's more like a different slope. Or if I smooth this out, it would be more like a curve. So the rate of degradation appears to be increasing as time goes on. Nevertheless, this is my linear model, and I'll force the best fit line, and I end up with a shelf life of 593. Now keep this in mind, because I want to compare it to what we get when we actually fit a different kind of model. And then before I get to that other model, though, the residual plots for this example, while there doesn't appear to be any issue with normality, you could kind of see that curvature in the relationship based on the fact that the model's like under-predicting at early times and late times and over-predicting in the middle. Okay, so there clearly is more of a curvature related to this degradation. So I went ahead and I'm using a different regression module in the same software that's not specific to shelf life problems. I don't necessarily get all the nice features, but I'll sort of make it work. So here it's called a fitted line plot. You can fit either a linear or like a quadratic model, which adds a squared term, time squared, or a cubic model, which would have a little more flexibility. But in any event, the quadratic model seems to work pretty well here. In fact, if you compare these R-square values, which are statistics which predict the amount of variation in the measurement that's explained by the model, here we're at almost 94%. On the linear model, it was down around less than 90%. So kind of doing a better job. And just to me, the mean line is more pleasing because at least it's going sort of through the middle of the data for the most part. And as before, we have some confidence bounds on this plot. Now the question remains is, at what point will my upper confidence bound intersect 50? Okay. It's going to be earlier than what the straight line predicted. The straight line kind of looked like this, so that predicted something out here. So that was sort of, the fact that we tried to fit a linear model, it would have given us a very optimistic shelf lifetime. It doesn't reflect the true nature of the degradation. So here's the quadratic model. If you're not sure whether quadratic is useful or not, like should I go to a square, you can always try it. And basically the p-value here on the ANOVA table is saying that both the linear and the quadratic terms are useful. Okay, because the low p-value, less than 5% here, indicates that we will reject the hypothesis that the quadratic term is like useless. It is useful. And my residual plots look quite a bit better when I fit the quadratic model. And then I want to figure out, like, where does this cross? Now, because this is not a shelf life module, it doesn't know that it should extrapolate. So one thing I can do is just do some predictions. So you could say, all right, here's my model, and then predict the mean value and the upper bound or lower bound. This is the plot always shows both bounds, but in prediction I can just say, give me the upper 95% confidence bound, for different times, and just iterate until you find it equaling 50. So that's what I'm doing here. So I started at time 500, and my upper bound is at 45 roughly, and then I increased to 510, and I've increased, but still not up to 50. And so I just sort of keep doing a prediction in my software until I'm very close to 50 at a setting of 530 for time. 540, I'm over 50, so I could go back and iterate some more, or I could just say, hey, it's 535 or something. So again, I'm looking still at where the upper 95% confidence bound, in this case on the mean life, crosses 50. If I wanted to look at other percentiles other than the 50th percentile, I think I'd probably have to go to the reliability module and model that in there. All right, so those are a bunch of different iterations of stability studies using, a certain percentile, a certain confidence bound, linear models, nonlinear models, also accounting for batch-to-batch differences and either pooling the data or going with the worst case. Now, the last modeling type I want to talk about is like an extension of the stability study, where we determine that, even to get some degradation, perhaps, we have to use some accelerating factors. So it is possible to, set up groups of units and essentially conduct a stability study like we just did, but at groups of different stress conditions. Again, high stress, medium stress, stress, all that are above the normal. And then you'll observe the degradation over time. And for each unit that you're monitoring over time, this assumes that you can measure the same unit over time. If not, you're going to have to put more units on test and test them at different times. But what you'll do here is actually fit a model just to the data from that single unit, and then predict when that unit will fail at that particular stress condition. And once you do that for all the units that are started to degrade, you actually have groups of predicted failure times at different stress conditions, different distributions. Then you can go back and do what we did before in the previous method. You can do an accelerated life test analysis where you model the distribution and relate it to stress and derive a distribution at the normal use condition, and then look at the reliability function and get your shelf life estimate from that. So it's a little bit more complicated because first we're using like a stability model, degradation model on the degradation data for each unit to predict failure times at different stresses. Then we're doing another model, really two more models. We're fitting like a Weibull distribution to the failure times. And then we're doing another regression model which relates how does the time at which, 1% or 5% fail, how does that depend on stress? So not sure in this version of the talk if I have a picture. I think just given the length of the material, I had to take it out. But again, when would you use this? When to even observe degradation within a reasonable time frame, you can't use normal. It would take too long to use just normal storage conditions. You would need some kind of acceleration. But so by doing that, you observe degradation, and then you can hopefully model that and derive those failure times. So this requires, again, that you're going to define failure as some level of degradation, like 50 in my example. Each unit or sample is going to be repeatedly measured. You'll fit the degradation or stability model for each unit, extrapolate to the defined degradation level, and then take those failure times and then go back and use the accelerated life test models we talked about earlier. Okay, so let's just summarize a couple things here. So again, we went through these sort of like a couple different ways to analyze the data, the life data analysis, and then accelerated life testing. And then we talked about regression modeling of the stability data, and also these accelerated degradation models plus accelerated life testing. They're broken across testing under normal conditions or stress conditions. Now, I just want to end with a couple of key points here. A lot of the models we talked about today involve extrapolation. And, you know, as a statistician, I'm not necessarily going to be comfortable with the science that says this model should continue, and, you know, unless there's scientists or engineers say, yes, we know that relationship, it'll continue. There are a lot of specialized models in this field of accelerated testing, for instance, like the Arrhenius temperature model and others that sort of have been shown to hold for certain stresses and certain kinds of products. Food scientists may have some of these models that you may have some faith in, so certainly think about using those. But to be really comfortable, I would say, you know, you're going to get these estimates based on extrapolation. It'd be nice if you could do some longer-term testing at normal conditions and validate that the models are giving you reasonable results, okay, at least one time. And then you could have more confidence going forward in future studies. Of course, the further we're extrapolating, either on the stability study or on the accelerated life test model, the more uncertainty there will be in the estimates, and also the greater risk that that the model may not be the right model across the full range that you're trying to use it. So that suggests that maybe we want to try to do sensitivity analysis, which is actually trying different types of models like linear, quadratic. Now, that may not give you very different data if the data you're looking at is clearly linear. I mean, the quadratic model is probably not going to look right, but sometimes, you know, you could fit one model or the other, and like especially if we're talking about which probability distribution fits the data, often more than one model will fit, and yet the results may look different. So depending on, you know, what we're doing, sensitivity analysis is going to be a good idea to look at how do the results vary depending on which model I'm fitting. The confidence bounds that you get on your estimates do not account for the uncertainty in which model you should be using. Another thing I'll just mention is that, you know, the software you're using may make it easy to do what you want or may not provide all the functionality. So you may need to get something that's, if you want to do accelerated life test models, then you'll need software that can actually handle that. Okay, lastly, when you select, you know, your units from like samples to put on a stability test or a life test, I encourage you to consider selecting specimens, not all from the same lot or batch, but to spread them across lots that you think would have as much variation as you would ever see. Maybe they were produced at different time points, different production conditions. The goal is to estimate the shelf life for your product and not just a single batch. So if there's variation from lot to lot, you kind of want that variation to be reflected in the analysis so that at least your confidence bounds are going to reflect the uncertainty. We didn't talk a whole lot about sample size, but that's like a common question. How much data should I put on test? And it's actually in this problem of shelf life, it's kind of a difficult question to answer. It's not as straightforward as, oh, I want to do a 2-sample t-test. How many units should I measure? to detect a difference of a certain amount given this standard deviation. I mean, there's a lot of sample size problems that are very straightforward. This one, the sample sizes that you actually need to estimate with a certain precision are going to depend on how much variation you have in the data and what model you're fitting. So you could play some, like do some simulation what ifs to get some guidance on that. And then, other things you need to worry about in the planning, like we talked about, is how frequently am I going to sample? When am I going to sample? That's going to depend on the approach you're using. If you're testing to failure, I probably wouldn't waste a whole lot of time measuring, at early times. I'd kind of wait till I get closer to when I expect units to fail. Those kinds of things. Versus if you're just going to get some initial degradation and do stability, then you're going to want to make sure you're testing